In physics, you would often like to simulate on a computer the dynamics of quantum systems that you actually have in nature. And for the same reason for which it is hard classically to find the ground state of a quantum system, it's also hard on a classical computer to simulate the dynamics of a quantum system, so the time evolution of a quantum system. Quite generally, you all know that the time evolution of a quantum system is described by a unitary operator. Every unitary operator can be written as the exponential of an anti-Hermitian operator, which I called A here. And in the particular case of time evolution, this anti-Hermitian operator is the imaginary unit times the Hamiltonian times the time parameter. Yeah? So and Planck's constant, of course, is involved as well. Yeah. But for the remainder of the discussion, for simplicity, I would like to use that notation just with an A in the exponent. So that's an anti-Hermitian operator. Say if you are given an initial quantum state and also you're given a duration t, and you want to calculate the state after time t, so you have to apply this unitary operator to your initial state. As I said, this is classically a hard problem, and unfortunately on a quantum computer as well, if we talk about completely arbitrary Hamiltonians. There is, however, an important class of Hamiltonians where on a quantum computer we can do better, namely n-particle Hamiltonians with local interactions. And this is fortunately a situation that we have quite often when we talk about when we have real quantum systems. We have particles that interact with each other at relatively short range. Yeah? So they interact with each other only locally. Yeah? Or we have, I don't know, in solid state physics, we have an Ising system, so elementary magnets, for example, and they interact with each other, but only nearest neighbors, or sort of the next nearest neighbors, but a finite range of interaction. In that case, we have local interactions, and I would like to show you that that situation can be simulated efficiently on a quantum computer. Let me first specify a bit more formally what I mean by local interactions. So in general, this exponent in your time evolution operator can be written as a sum of various contributions, AI, and each contribution has a tensor product form, which sort of each factor applies to one of the n particles. So we have n factors. Yeah. I'm assuming here that we have distinguishable particles. Yeah. So I can identify the particles. The first factor refers to the first particle, and so on. And some of these factors might be trivial, just unit operators, and some factors might be non-trivial operators, AI, which are marked then with an upper index that refers to the label of the particle. Now I say that the interaction is local if in such a contribution the number of non-trivial factors is at most some k, some upper limit k, where the k in turn does not depend on the total number of particles in the system. Yeah, so if I think again of the elementary magnets in a solid state system, in a crystal, say, then let's say each magnet interacts with 12 neighbors. And regardless of how many magnets there are in total in your system. So the important aspect here is that this number k does not scale with the total number of particles in your system. One also says that each particle couples to at most k-1 others, independently of how many particles there are in total. Now, in general, when you have such this limitation, then in your sum you can have all possible combinations involving k out of the n particles. So the number of summands in your sum scales with the number of ways in which you can pick k particles that interact with each other out of the total of n particles. So the upper limit in your summation index, the L, scales with that number of ways for picking k out of n particles, and this, you know, from combinatorics, is the binomial coefficient n over k. And for our purposes, it's enough to note that this scales polynomially with n. Yeah, assuming that k does not scale with n, then this binomial coefficient scales polynomially with n. Now, after these preliminaries, let's come to the core of the argument, and that involves a particular approximation that's called the Suzuki-Trotter approximation. And I'd like to explain to you briefly the basic idea. When you exponentiate operators, or a sum of operators, then in contrast to exponentiating numbers, the exponential typically does not factorize unless all the operators commute with each other. So the exponential of the sum that we had on the previous page is in general not the product of exponentials. There's, however, a clever way of getting to something similar, and the idea involves the so-called Suzuki-Trotter decomposition, and that is, in the first step, to write the exponential of a as the exponential of a over some number s, and then take this whole exponential to the power s. And if you can make this s as large as you like, and so basically within the square bracket you then have sort of a tiny unitary transformation. Yeah, so basically on the left hand side, the exponential of a, that's our entire time evolution, that's some unitary transformation. And on the right hand side, inside the square bracket, you have just a very small unitary transformation, yeah, can imagine sort of rotation by just a very small angle. And then you take that, you do that s times. So basically you decompose your big unitary transformation into s small steps. Now it turns out that within the square bracket, so if the unitary transformation is tiny, then to a good approximation you can factorize that. Yeah, so now you have on the right hand side, inside the big square bracket, you have a product of individual small unitary transformations, and each of these is just generated by one of the AIs. Yeah? So here we applied to the small unitary transformation within the square bracket, we applied the factorization. And that's a good approximation, and it gets better the larger the s. But of course it comes with an error, and the error are the remaining terms that you have on the right hand side. But let's stick for the moment with this factorization. And what we have effectively done is we've decomposed the big unitary transformation into a total of, first of all, in the first step, s small steps, and then we further decomposed each of these s small steps into l small steps, yeah, corresponding to the AI, of which there were l. So altogether, we've decomposed the unitary transformation into s times l small steps, and each of these steps is generated by just one of the AIs, and therefore involves only local interactions. So we have s times l small and local steps. There's a little Mickey Mouse representation of this idea. Imagine you have a unitary transformation generated by the sum of two operators a and b. So you have the exponential of a plus b. This unitary transformation, that's the long diagonal arrow pointing towards a plus b. And since when a and b do not commute, then you are not allowed, as is suggested by this parallelogram, you are not allowed to first do e to the a and then e to the b. Yeah, so this is not allowed. But if you decompose it into small steps and you create this type of staircase, then it becomes a better and better approximation. As then you basically you go along the diagonal arrow, and you do that sort of like a staircase, and the smaller the steps in your staircase, the better the approximation to the overall unitary transformation. Yeah, and each little step on your staircase corresponds to one of these small local operators in the formula. Now, in terms of resources, computational resources, since each individual local step involves only at most k particles, and the number k does not scale with n, this means that simulating such an individual small local transformation requires resources which do not scale with n, because only k are involved, k particles are involved, and k doesn't scale with n. Yeah. So effectively, if there was no error, we come to the error in a minute, but suppose there was no error, and this was an exact formula, then we'd have S times L small steps. The computational resources required for each step would not scale with n. And of course, the overall resources then would scale with S times L. And we have yet to see how S times L scale with n. And this leads us to the next step, namely considering the error. This is an approximation, so we are not aiming at an exact calculation, but we want to simulate our quantum system, our n-particle system, to a good enough approximation. Good enough means that we specify some maximum error that we allow. Yeah, so we specify an upper bound for the error. And then we ask how many resources do we need in order to achieve a simulation whose error does not exceed this upper bound. Yeah, stays below this upper bound. So let's have a closer look at this error. There are two terms here. There's a sum of commutators and a prefactor 1 over 2s. So this first contribution scales with 1 over s. And then there are further corrections, further terms that scale with at least 1 over s squared. Now in the first step, let's say that the s is so large that we can neglect anything of the order 1 over s squared. And we focus on the leading contribution to the error. Now, that scales, first of all, with 1 over s, because that's explicitly the prefactor. And then the operators AI, the individual AIs, they do not scale with n. But what we have to do is we have to count the number of terms in the sum, and we have to investigate how the number of terms scales with the number of particles. Remember that we had L terms in the exponent. Yeah, so the index I of the operators AI, that ran from 1 to L. And then you can look at how many different commutators are there. Yeah? So you have pairs of AI and AJ, where the number of different pairs, that scales then with L squared. On the previous page, we saw that L, the number of terms in the sum, scales polynomially with n. And this means that L squared also scales polynomially with n. And therefore the number of terms in this sum here in the error scales polynomially with n. So taken together, this first contribution to the error scales polynomially with n and with 1 over s. And all the higher order terms in the error we said we wanted to neglect. And we want the error to be smaller than some upper bound, which I would like to call epsilon. Now remember, the motivation for investigating the error was to find out how finely we have to divide the unitary transformation. So how large we have to choose the S. So if we have the requirement that the error, which is of the order polynomial of n over s, if that shall be at most of the order epsilon, then solving for s, we find that s must be at least of the order polynomial of n divided by epsilon. Now the epsilon itself, that's a fixed bound which does not scale with n. So essentially s, the required s, scales polynomially with n. Now remember, on the left side of the expression, so where we have the many small local transformations, we have s times l terms, s times l of these small local transformations. We just found out that the s that we need in order to stay below the maximum error, the scales polynomially with n. We saw already on the previous page that the L scales polynomially with n. So the product of the two, S times L, also scales polynomially with n. So this means that the number of small local transformations in which we decompose our big time evolution operator, that the number of small steps scales polynomially with the number of particles. And this means that the overall resources that we need also scale only polynomially with the number of particles. Because as long as we stay below the epsilon, the upper bound for the error, so that was sort of our requirement. We stay below a given maximum error epsilon. Then we have S times L small local transformations. This number of transformations, S times L, scales polynomially with the number of particles, and each local transformation by itself is independent of n, requires resources which are independent of n. So overall, the resource requirement scales polynomially with n. And this means the simulation is indeed efficient.